round out the afternoon by talking a little bit about metacircular VMs, which originate from mostly from two causes, and the more important one is to try and avoid using C or C++. And there are a whole bunch of problems that you've probably encountered in your own VM development from using C or C++. And there's kind of this laundry list here, so in no particular order, but you go through these. So one is, C and C++ are not type or memory-safe languages. That's good when you're doing something like writing a GC, because you need to bend the rules and do strange bit manipulation, memory manipulations. But that tends to be, maybe only 5 or 10% of a VM code. When you're writing the compiler, you don't need something that's breaking those kinds of rules and doing funny casts. And so the lack of safety there just makes development that much harder, because it means that when you make a mistake, you don't find out about it until runtime or worse. So that's been an issue in terms of productivity. Another issue has been that to build a VM using C or C++, you usually have to break the rules in a way that relies on some kind of unspecified property, something that a particular compiler does, a layout that it adopts, which if that happens to change in the implementation, then you're hosed. So I showed you, for example, the way vtables were used as map pointers in the self-implementation of years ago, and that's a completely it's completely non-standard. The language spec does not guarantee that behavior in any way. And so if you took that exact same source space and compile it with a different C++ compiler, you'd find it wouldn't work, as I, in fact, encountered years ago. That's a couple of problems. The second, and perhaps the more serious one, is that if you develop in C and C++, you're using this black box compiler, which is compiling everything ahead of time, and which you can't really get into the internals of in any straightforward manner. So, for example, if you want to find out where all of the pointers are on the stack, well, it's not going to tell you that. It doesn't keep that information typically, and even if it did, there's no API for getting it out at the end. People have tried, for example, using ELF debugging and other debugging information to get that kind of stuff, but in general, it's not reliable enough. The accuracy there for a debugger is rarely good enough to build a garbage collector on. So you've got this sort of closed world which you can't introspect on in any easy way. And also, you typically can't generate code at runtime through the C or C++ compiler. Either there's no API, or if you can devise one, the compiler is typically so slow that it's not really practical as a runtime compiler. So you have to build your own compiler anyway, because of those problems. When you do build your own compiler, or you have an interpreter, then you have to deal with adapting between the calling conventions of your compiler and the calling conventions of the C compiler. Click listed a whole bunch of problems there, things like floats being in the wrong places, stuff like that. There's certain things that their C compiler just doesn't do for you, like it doesn't do Stack Overflow checks. So if you're building a language that's safe in the stack, then how do you deal with calling into the C runtime? If that happens to cause the overflow, it's very difficult to deal with that. So there are all sorts of issues there. The memory model of the language is often a mismatch from the memory model of the language you're implementing. While it's low level for most purposes, for some purposes it's not low level enough. Many of the examples I showed you illustrating things like inline caches, I had to express an assembly code because there is no C mechanism where you can express those and get the machine code that you would want. So it's kind of too low level for most of the VM, but it's not low level enough for some parts where you really want to fine tune the individual instructions and get exactly a particular sequence. And the result is building a VM in C and C++, a high-performance one, requires extraordinary skill and a massive amount of effort. As hopefully by now you'll comprehend. It takes a lot of work to do this and make something that works really well and that's reliable enough and portable enough for production use. So a number of people have instead tried to go down another route by writing VMs in other languages. Typically a higher level language which has better data structuring and safety properties, so that when you write things like compilers, you can take advantage of those properties and get more productivity from the fact that errors are caught sooner, or that you can build nicer abstractions than you can straightforwardly. Certainly in C, it's very difficult to build good abstractions. C++ makes it a little easier, but still by no means ideal. Sometimes the attempt has been also to provide features which give you the low-level control when needed to avoid assembly code. It'd be nice if you could have both at the same time, to be able to be higher level but dip down for low-level control when you really need it. And what you'd also like to have is very uniform handling of all of the things, the nitty-gritty that the C compiler is not going to take care of you, locating pointers, placing safe points in generated code, bridging calling conventions, things like that. And ideally, if that stuff could be done for you automatically, so you write an implementation that deals with those in one place, somewhere in a language implementation, and then in the actual code of the VM, you don't have to worry about those things, because the language that you're expressing the VM in automatically takes care of that. That would be ideal. So those are the kinds of things you would want to get. The alternate direction, which kind of isn't related strongly, but it's worth mentioning briefly, is the desire of building stacked implementations in a higher level language that run on an underlying VM. So this is another way of building a language implementation, which is just reuse somebody else's VM and map onto it. In theory, that sounds like a good idea. In practice, it's somewhat varied. There have been a whole bunch of these attempted. So there's Wikipedia pages that list all the JVM languages that run on top of the JVM, all of the CLI languages that run on top of the .NET CLI. There have been a bunch tried much earlier than that. A couple that I worked on long ago, Smalltalk in Self and Java in Self. So it's not a new idea. It addresses the safety and abstraction issues if you get to reuse one of these higher level languages, but it doesn't really deal with any of the other issues. And the difficulty is, of course, when there are semantic mismatches between the thing you're implementing and the VM that's underneath. Often that either compromises performance or induces some horrible complexity, or often both. So the path that's been tried most commonly to get a high performance VM expressed in a more suitable language is to build what's called a meta-circular interpreter. The approach I'll describe has a particular compiler architecture to it. You can also build meta-circular interpreters just by writing an interpreter for a language in itself and running it on its own VM. And that has been done. So for example, if you get the Smalltalk definition from the early 80s, in the back there is a Smalltalk reference implementation written in Smalltalk. There was a Java implementation done at Sun Labs by a colleague written in Java that runs on a Java VM. That's certainly possible, but there's a massive performance penalty to be paid by having that extra level of interpretation. Yes?
The sick people that a lot of people go through for 61A kind of does that with speed.
Okay. Does that have the same kind of slowdown? Yeah. So 100 to 1,000. I looked up, there's a technical report on the Java and Java implementation that was done in the late 90s at Sun Labs, and I think they measured a 700-fold slowdown in running. But they could run stacked, and they even ran stacked on top of the stack with another 700-fold multiplier on top of that. So that's not the way we want to go. Now, another way you could go is sort of avoid the issue of doing your own thing by doing everything in C. Compile to C. Don't just generate. Don't just handwrite the C. Generate C from some kind of higher level language. That's another tack that's been taken, and this has been tried in a number of different VMs. The inspirational example here is the Squeak VM that was developed in the late 90s for Smalltalk. That's been emulated a number of times in different scenarios. And the attractions here are, firstly, that you leverage the fact that C is universal, right? Pretty much if you have a processor, the first thing that's going to appear on that after an assembler is going to be a C compiler. And so you can leverage the fact that there's a C compiler and avoid the low-level machine details by using C as a portable backend. It doesn't address some of the low-level issues, the conventions, the fine-tuning of instruction sequences, but you can build into the translator things like the OOP tracking code that is needed by the GC. So you can put the expression, the tracking of the variables on the stack into the thing that generates C from your higher level language. And so then the higher level language, you don't have to worry about that stuff in the bulk of the VM code. As I mentioned earlier, C compilers are typically too slow to be used at runtime. As a dynamic compiler, you end up with a beta that's enormous, so that you'll never amortize a compilation except in very exceptional circumstances. People are trying this now with LLVM fairly seriously. There have been a bunch of attempts using LLVM as a dynamic compiler for a variety of languages. It all depends on what you're compiling and how long your programs run and what the overhead is. Some systems they've decided it's just too slow. Others seem to be using it fairly happily. So it's kind of a mixed bag there. It all depends on your situation. Let's look at the Squeak in a little bit more detail. So Squeak was a Smalltalk system developed in the late 90s by several of the original Xerox Smalltalk pioneers and some other folks, all while they were at Disney. And it's implemented, similar to the PyPy approach, it's implemented in a subset of Smalltalk. So PyPy takes Python and takes a subset of it, which is able to express the constructs that are needed and yet still be efficiently implemented. Squeak takes a similar approach. They have a subset called Slang, which is a fairly restricted subset of Smalltalk, and they use that to express the basic definition of the virtual machine. It's based on the Blue Book definition, so it requires, if you look at that, it requires actually very little of the sophistication of Smalltalk. It's fairly straight ahead. Loops and tests and method calls. One of the advantages of that is that because it's written in Smalltalk, when you run it on Smalltalk VM, you could do the development of your VM in Smalltalk at a performance penalty because it's being run interpreted on the underlying thing, but it is still a very malleable implementation. But then what they do is they're able to translate it fairly efficiently to C and then compile the C to make a new VM. So the development cycle is that you work within the VM, developing sort of an emulation of the VM at poor performance, but when you're ready, you push the button, a bunch of C gets emitted, the C compiler cranks up, a new binary is emitted, and then you can test the new VM. So it's a slightly extended development cycle. Notice that because of the problems with using C as a dynamic compiler, even though Squeak, since this original implementation, the original implementation was an interpreter. Since then, various JIT compilers have been developed for it, but none of them go via C. They all just directly generate machine code. This particular system also inspired a similar Java virtual machine developed at Sun Labs called Squawk, and that was used in Sun's sensor platform that was developed and deployed in the late 2000s, and had the same sort of advantages. It could generate something fairly small and self-contained. So, but what we really want to talk about is how to get a metacircular implementation that has good performance, which means sophisticated compilation, and as well as being expressed in a language which hopefully is more productive for writing our VM. So the approach, which has been used in a variety of systems now, is to use an architecture in which a single compiler for the language in which you're expressing the VM can be used both to build the VM statically and can also be used dynamically to compile the application that's running on that same VM. So let me run you through a little movie that demonstrates how this is done. So let's start, I'll do an example, I'll quote some Java stuff I think in this, just to make it concrete. But let's say we have a pre-existing Java VM. We have our bytecode compiler that takes source and generates bytecodes, which of course has been compiled through itself previously, so that's the green thing here. And the first thing we do is we write a compiler for our language, in this case Java, which is going to generate machine code, not bytecode. So this compiler is probably going to take Java bytecode and it's going to generate machine code. So it's a binary compiler. That's the source that's in the top. And when we run that through our bytecode compiler, out pops the bytecode, of course, for that compiler that we ran. So now we can take the bytecode, run that on top of our VM, and feed it the source of our compiler and the source of our VM together. And that will then pop out a binary, because it's a compiler that generates machine code. So it's going to take the source of our VM and generate the binary, and then on our binary we can take our application bytecode, run that on top of the VM, and of course inside that VM is the very self-same compiler that's compiled itself, and that can generate the machine code at runtime that's going to execute our application. So that's the approach that's been adopted. It has some advantages. We're using the same compiler for the VM as the application, which means there's a common uniform calling convention throughout. We're not dealing with some foreign calling convention. Because it's the same compiler, if we keep enough information around, we can inline VM code into our application, when the application calls into VM primitives. We don't need to have a hard boundary there. That can be a soft boundary now, which is open to the compiler. And we have a common framework now for handling things like save points and hoop tracking and such like, which means we build that stuff into our compiler once, and the source code of our VM, for the most part, doesn't have to worry about that. It's taken care for us. Now, there are some complications. So we still must be able to write a runtime, including a garbage collector. So you can't do that in Java as it stands, right? If you take the standard language, there's just no mechanism for building something like that. And so we need some unsafe language features, some extensions for which we're able to manipulate memory. And even with that, life is not necessarily going to be so straightforward, because we're writing a garbage collector in a garbage collected language. And so we have to use a subset of that avoids allocation, or that if it does allocate, allocates in a very constrained way, which isn't going to step on its own coattails and cause problems. So there's kind of, I could probably spend a month on this one bullet point alone, but doing the GC in a GC language is tricky. There are all sorts of complications that induces, which weren't there before when we wrote them in C and C++. So that's a downside of the approach. Let's look at some examples. The most well-known one for sure is the JIKES Research VM, which was initially known in the papers as Jalapeno, developed by IBM in the late 90s as a research vehicle. It's been open sourced, has been used very widely in academia for Java, VM research, and other language implementation research. So there's literally hundreds of papers out there where they've used this system as the basis for the research. And it's written in Java. It's a complete Java VM written in Java using the framework that I just described, that approach. But they've enhanced the Java with some magic to do the GC work and the other non-safe operations. So it includes a very flexible and rich GC system, a system called MMTK, which was, I think, originally written in C or C++, and then was ported and contributed by academics into the system. And that gives them a whole bunch of very well-defined, flexible interfaces for building garbage collectors. And there have been a bunch of different garbage collectors implemented to these interfaces, so you could sort of mix and match a wide variety of different GC algorithms in JIKES. There are a whole bunch of different implementations there. It uses at least 2 compilers. If you look at the original paper, they had 3 compilers, for no obvious reason that I can discern. But 2 at least are required. There's a baseline JIT compiler that's used for simple execution of bytecodes. And then an optimizing compiler that's used at runtime adaptively to run optimized code. There's no interpreter in this system. It has the sort of similar framework to the ones I've described in previous lectures for detecting hotspots and doing dynamic optimization and de-optimization and on-stack replacement. All of that is basically more or less the same as the systems that I've described. The big difference in methodology is that you write your system in Java, and then a VM builder takes all of the code you wrote, compiles it up, and part of that code is run to generate an initial heap, and all of the code and the objects are dumped into a heap image. And then when you actually run your VM, all it does is basically initialize the heap with the contents of this file with a tiny little shim that's written probably in C, loads that into memory, and off it goes, and it's kind of this self-contained world. During the process of writing that image out, a process called tree shaking is used, which finds methods that you might have written that are no longer required in the target image. So, for example, if you're building something for production use and you don't need all the debugging support, you can strip all of that stuff out. There might be other code that's there that's just infrastructure that's not required in the final image. So all of that can be shaken out. If there are fields in objects that are no longer referenced, those can be eliminated, things like that. A whole bunch of static optimizations that can be done to make the final binary version of the VM smaller and faster. As for the extensions, well, so the first thing to notice is, you're implementing the language, so you can add anything you like because you're the implementer. You don't have to worry about what the committee says. As long as the end users can't see the extensions, you can put anything you want in. And that's sort of the power of this approach. You sort of sprinkle in whatever new features you need. The way it's done typically is there's sort of 3 components to it. One is you add data types to access the kinds of machine level entities that you need to manipulate in your program. So you might build in a primitive data type that's recognized by the compiler for a machine word or a pointer, which enables you to do address arithmetic. Then you need to add methods into those types or the classes that allow you to do operations on those things. And typically these methods, there's a signature available in the class library, but the compiler just knows what those things are supposed to do and intrinsifies them, just emits the machine code directly to do what the underlying operation is. And finally, all of that stuff gets wrapped in layers of typing and annotations typically to make the intent very clear as to where you're using them, and when you're being unsafe, that you know you're being unsafe. So typically you have to write some kind of declaration that says, I really know what I'm doing here, please don't get in the way. I'm manipulating bits of memory. And so typically part of the build process will check those annotations to make sure that when you're using the unsafe stuff, you've said you were using the unsafe stuff and it's not leaking to places where it shouldn't leak. And the compiler is typically moded so that that stuff isn't available to end-user applications. So when the compiler is embedded in the final VM and it's running some end-user application, it can't call into all this stuff and subvert type system. So there are other annotations that are often interpreted by the compiler. Again, you're implementing the language, so you can recognize anything you like. Early versions might have used structured comments to do this. More recent implementations typically use Java annotations. And the annotations can be used to do things like drive the inlining, give hints, because of course the compiler is running statically, and so it can't use adaptive optimization to optimize the VM. It has to do a good ahead of time optimization, and so giving it hints for how to do that is important. You might have other annotations for bootstrapping purposes that say, you know, this code is to be evaluated while you're writing the image, but once you're in the image, it just evaluates to something else, a constant, or the result of the earlier evaluation. These are sort of extra-lingual features that you need to describe these two phases separately. And similarly, when you're writing the garbage collector, you need to exclude things like save points from being generated or interrupts or whatever. And so there'll be annotations that you can write there that direct the compiler to not to do certain things that it would do for user code. Another VM that used this overall kind of approach, but was very different in style, was the Klein VM, which was done by Dave Unger and some other folks at Sun Labs, which was a self VM written in self. And the idea here was quite different. The goals were different. The idea was to be able to write full self code and have that generate a VM image by basically taking the world of objects that have been created in self and having them written out, exported, using a different interpretation than the standard exporting representation, which is just used to exchange source. The exporter would generate bits which would be embedded in the final the Klein boot image. It used the same approach of building an image and then loading it with a thin C shim. But there are a couple of new things here that are worth calling out. In particular, there was a lot of attention paid to the debugging story. So one of the things that's really difficult when debugging, so as you've already experienced, when you're writing a CVM and some of your code is an assembler and some of it's JITted, the debugger doesn't often give you a very good story as to what's going on in the middle of your execution. This only gets worse when you're generating code from a compiler that you wrote, because now you have no debugger for that typically. Because debuggers for Java are used to connect to VMs. They're not used to debug statically generated Java code. So you either end up having to build your own tool chain to do all of that stuff, or in this case, the way they did it was they used one self world to debug one that was being bootstrapped up in a different image. And so the idea here was to provide reflective proxies, which were already present in the self world, but re-implement them so that they could proxy to similar objects that were running in the other image. So it's kind of an RPC style model of proxying here. And it gave them a very rich debugging environment in which they could inspect the state of a running VM using an existing VM, look at what was going on there in terms that were much more easier to understand than a low-level memory model of hex dumps and such like, and even modify, fix and continue stuff and run it. So that was sort of an inspiration, and got picked up, as you'll see, in the another project that was done at Sun Labs called a Maxine VM. So Maxine was sort of inspired by Klein. This was another Java VM written in Java. I'll show you a picture of the architecture in a second, but the novelties, I want to call it, in this system were the way that the JIT compiler was built, the way that some of the optimization stuff was implemented, and again, the debugging story. So here's an architectural picture taken from the main Maxine paper. Most of this stuff, if you look at it, you should recognize, right? All of these terms should be more or less familiar. You've got a stop and copy garbage collector and a heap, baseline code. This is the baseline compiler, optimized code, an optimizing compiler, de-optimization, stack walking threads, locking natives. All of this stuff is fairly standard. The interesting parts I want to talk about are the way the baseline compiler was implemented, some of the tricks used in the optimizing system, and also this debugger, out-of-process debugger that was used. So let's start with the template JIT. So the first level execution in this system is not via an interpreter, it's via a template JIT, similar to the one you've implemented. The interesting thing here is that the templates themselves are written in Java, and they're not handwritten in assembly code, they're written at a higher level and then fed into the optimizing compiler that's run ahead of time to generate the machine code for the templates. And in fact, the compiler is modified to know about this template stuff and to take extra annotations, which are used in connecting these things together, basically generating the metadata that's used to stitch the templates together when you generate the final version of the code. I'll show you this example, again taken from one of the papers. This is the Java code for the integer array load bytecode here. So this is, it's not a piece of assembly code. It's this fairly high-level stuff, and it's conventional Java code. There are these extra annotations that describe stack slot information that are processed by the template processor. Here's an annotation that declares that it's a template for the template JIT, which bytecode it's implementing. There are annotations that guide the optimizing compiler to do inlining, because all of this stuff gets evaluated, most of it gets evaluated ahead of time. And then you can see the code for the actual bytecode itself looks fairly high level. It's calling these operations, which are low-level primitive operations, like get an int from an object. So here's an object being manipulated as a reference. So this reference type is specially understood by the Maxine compiler. And this get int operation says I'm going to get the ith int out from this array, and the layout of objects is parameterized in things like schemes that are sort of basic building blocks of the system and are easily re-implemented. So if you want to change the layout of a particular fundamental type in Maxine, you go in and you find one of these layouts. There are multiple ones in the system, and you either implement a new one or you select one of the pre-existing ones. So you can have all sorts of different customized pieces and get the each of these pieces has an interface which isolates it from the rest of the system, so switching one out doesn't mean that you have to go through your entire program looking for all the asterisks, dereferencing the pointer and change them to use something else. So this gives you a nice structured way of building the system, and fairly high-level code that's used to express stuff in a portable way. There's no sort of hint of machine architecture at this level. That's all isolated in the optimizing compiler that processes this and generates the templates. So when you actually run the template compiler on this, you get this code, which is not super efficient, but it's not bad for a template JIT. And it's done all of the usual stuff and moved the stack variables in and off the stack and generated the tests and the branches and the exceptions and all of that stuff. So it's a pretty reasonable template, but that's generated, it's not handwritten. Okay. Another interesting feature that was introduced with Maxine is to address the issue of when you write an optimizing compiler. So when you have a VM with an interpreter or a simple JIT and an optimizing compiler, typically you end up with 2 or even 3 different implementations of the same thing. You have a direct implementation of some operation that's in the interpreter, ready to be called when interpreted, or directly from the JIT as part of the runtime. So this might be some support routine. And then often you will have the meta version of that expressed as code that generates that code in the optimizing compiler. And the way it typically will do that is it will have to hand construct the intermediate representation for the thing that you're compiling and stitch it into the graph. If you look, for example, in the hotspot server compiler, there are some just scary as hell pieces of C++ code that do this, for common sequences, where it's basically, if you imagine you're at the edge of a graph that's being built, and you're stitching together a new piece of graph, connecting up all of the inputs and dangling out some outputs, ready for the next phase, the next bytecode to be compiled. And that stuff is just horrible to write. It's incredibly tedious and error-prone to get that stuff right. And it's incredibly non-malleable for if you want to change the implementation. So that was the traditional way optimizing compiler implementations of these implementations were done. You find similar code to that in JIGES as well as doing the IR stitching. But in Maxine there was a new approach that was tried, which has been given the name snippet. It's not a great name, but quite a nice technique. So the idea here is, well, if we're generating IR, we already have a tool that does that. It's called the compiler. But we have to get it to be able to generate IR that isn't from standard Java code. It has to express some kind of semantics, which are part of the compiler and not part of the source language. And so basically this is another language extension with annotations that allows low-level routines to be expressed using a relatively high-level language. And then what happens is a three-stage process in which initially the code that expresses the snippet is run during image building, and it generates a very generic piece of IR which is included in the image. And then as the compiler runs later, that's specialized for various different contexts. Typically these operations are used in several different places, and the context varies, often leading to constant folding based on the context. So there's some amount of simplification that can take place when that happens. And then finally, those specialized pieces of IR can be stitched in by the compiler to an actual compile when that particular operation is being inlined into a method that's being compiled. This approach was very successful. It's still in use in the Graal compiler, which we'll talk about next week. And there's a nice little example in the paper that shows it in use. So this is a fragment of Java code. I don't know if you can see this at the back, but it's basically doing a little bit of list processing, and here's the bytecode for it. And you can see required by the Java type system is a check cast, which is one of these operations that you have to implement. You have to be able to call it directly. You have to be able to generate it. You want to make it fairly efficient in most cases. And so the way that's expressed in Maxine is this thing that, well, I mean, it looks like Java, but it has all of these annotations which you won't recognize. There's an annotation that says we have a snippet, we have a method, we have other annotations that are used to communicate characteristics with the compiler. So for example, this parameter here, this particular code is going to generate an instance of test, but it's profiled. So we assume it's already been run through the template JIT, and we've seen a number of occurrences of this already. And the profiling has generated a histogram of types that have been seen already, and it's also generated whether we've ever seen a null operand here, which is expressed as this parameter. So we get this information from the other code that's gathering the profile. We do a guard that's probabilistic here. So if we think, based on what we've seen, that the object is likely to be null, if we haven't seen a null yet, then we're going to say we're not even going to bother compiling that. Here we explicitly enter the deoptimizer. So one of the interesting things here is that the compiler can explicitly invoke deoptimization in these snippets. So it looks like Java code, but it's this weird meta level description that says, okay, through here I might be compiling, but I'm not going to compile from this point. Here I'll be interpreting from this point on. There are other tests here to check whether it matches any of the classes we've seen. They're called hubs in Maxine. And there's an annotation here that says, okay, there's a loop following me. I want you to fully unroll this loop when you generate the code for it, so that we're just doing a series of task increment operations. And again, if we get to the bottom, there's an explicit invocation of de-optimization. Once all of that's being processed by the compiler and included in a real method, you see, you get a fairly explicit. This is obviously for a specific call site, it's not generic code. It's specific to that particular example before, but it's very tight code. You really couldn't do any better than this. And the result is we've written this fairly high-level description of an operation, which given the hints that we've got from the runtime system and being able to communicate decisions based on those hints back to the compiler, we can generate very efficient code for this specific example. Final thing I'm going to mention is the inspector. I said that Klein had a sophisticated debugging tool. This was taken to a much higher level in Maxine in the form of this inspector. So the inspector is a special purpose debugger used just to debug this VM. And the idea is, as you're building the image, you're doing the image writing and you're analyzing the source code and compiling the source code, you emit enough metadata that's sort of the equivalent of debug information, but it's much richer than a conventional debugging system, that allows the inspector now to connect to a running world and figure out what's going on inside it. So it allows it to attach and observe and debug and control the Maxine instance. And the real trick here is that it has to be able to do that even if the thing underlying it is broken. So if you've got a GC bug and some memory corruption, it mustn't break in itself when looking at this thing. So it has to be structured in this very disciplined way that checks for a particular property before it relies on that property in higher levels of the visualization code. And it can do, it can look at memory and show you it as raw bytes, or it can show you it as an object. It can give you descriptions of what's in the registers and stack frames and threads and such at very high levels of description that are understandable, as Java objects. So it's doing that sort of reverse mapping from raw bits in memory back out to something that's looks familiar to a virtual machine developer. This is actually best seen in demonstration. So this evening I'll send out a link to some YouTube videos that were made demonstrating the system. It's kind of cool. The videos are not of what you might call professional production quality, but I think you'll get the general idea. This was also partly inspired by a system developed for Hotspot called the Serviceability Agent, which did something similar to this, except it provided only a read-only view. You couldn't change and debug and continue in the VM execution, and that required, because of Hotspot being written in C++, it required a lot of additional C++ code in the VM to gather this metadata and emit it in a form that the Serviceability Agent could then use. So it was a much more of a maintenance burden than the Maxine inspector was. And the only other one I was going to mention was PyPy, but you've heard plenty about that, so I don't think I need to say any more. Hang on, 5 o'clock. Any questions, issues? Jit, all gone okay?
I have a question. When you're considering having Java with annotations as your special implementation language, how would you compare that to just writing your own totally new language?
The main advantage is you get the very rich tool chain that comes with a mature, widely adopted language. And one of the things they were very, very careful with Maxine, and when we look at Graal and Truffle next week, was not to do anything that isn't pure Java. no syntactic extensions. All the extensions come through the extension mechanisms that are already available, like annotations, because then all of the IDEs work. And you can, if you're very careful about how you specify your annotations and how you pre-process them, you can even get to a situation where you can build and run something on a stock VM for debugging. At least some part of it might be buildable and runnable. The story for that is much stronger for Truffle, which we'll cover next week. That's sort of a key result. But the main reason of going down that path was, to avoid having to build an IDE as well.
Okay.
And all of the other tools that do cross-referencing and documentation and source code repositories and all of that stuff.
Okay.
That's the price you pay for doing your own language.
Gotcha.
Okay, so see you next week.
Yeah. So